might be like, I thought I knew the answer to this. The question is, oops, force of gravity on an object, right? We gave you more specific and say force of gravity is the force of the generally the mass for a really long time, right? So far until today, talk about right? On an middle school and all that sort of stuff. And how do you measure it? Just acknowledge, we're just like, oh, it has such and such a mass, and then we plug that into stuff and whatever. What I want you to do right now is to think about what that means. I'm going to give you, I don't know, a minute maybe. Write down a definition. Do you have a question before we do that, or do you have an answer? Okay. All right. So the minute begins now. Write down a definition. And then how do you measure the weight of an object? It does. Yes. What's that? So this is you and your brain. I want you to write this down by yourself first. All right. What's a scale? Kind of maybe hard to define. Maybe not. Maybe it's super easy. Oh, was it have an answer? What did you come up with? It doesn't have anybody else agree? Do you think a scale is the right idea? What did you come up with? That's how I would measure weight. So yeah, matter. I'm sorry. Did you have a better answer? Do you not like that answer? I like that answer. Can you tell me a little bit more? Like, what's that? Okay. No, I'm going to cut you off. Let me ask the amount of matter an object has. Is this a scale? Period. End of sentence. Okay. Okay. I felt like I started talking right over you. That was just totally rude. So the amount of matter. That's a good question. That's why we're here today. What's the difference between a balance and a scale? What else? Other definitions. What is mass? High five for you. If it's digital, right? So what do you mean? Not all scales are digital. Okay, so an atom has mass. What does that mean?
Just the force applied whatever you set on it, whereas the balance, it has like known masses, which if you were to like put them on the moon or something, it would still have the same mass given by the balance, regardless of the lower gravitational force.
Does that make sense? I'm gonna put atoms in there too, just so we can kind of keep that. Think this through out loud too. Part of the if I was headed to the moon and I had 7 things to pack, I'd probably pack multiply by the number of them or things to put in my bag. Right. I take this to the at the frog because you got to measure the mass of the frog. I measure the mass of the frog on the Earth. He measures whatever mass he measures. I take this whole system to the moon. Is my value going to change? Is my measure going to change? So, no. What do you mean? His mass doesn't change, right? Tell me more.
Like mass?
I have a bathroom scale in the back, but I'm not going to go get it because you all have seen a bathroom scale, right? A little square you stand on. Okay. So I'm going to write that down because I like that. Mass is different. Okay. So I stand on that thing, or I put the frog on that thing, and it measures his what? But they're related. Wait, his force is what you're saying. Okay, now, so they're related, but they're not the same thing. And the way that they're related, it's really actually measuring the force that is being pushed up on him. Does that make sense? Okay. So weight. It's kind of like, when I put the frog on the table, there's a force of the earth on the frog, and there's also a force of the mass times. Well, if I put a scale in there instead, then really what that scale is measuring is it's measuring the force it's pushing up. Of. Okay. It uses a little spring. Okay, that's why they often call them springs. The force of so two objects, right? Calibrated for the Earth. It's calibrated for here. Has to do with the Earth and this one, yeah. If I take that spring scale generally to the moon, so and this is deep, right? This is like yeah. All my stuff is gone. Or the moon, or the sun, or the whatever. Right? They still do those scales. So weight equals mass. That have like the basket. Do you know what I'm talking about? That you put like your fruit in, like you put your oranges in there, and they like hang up like acceleration, and then they like tell you exactly how much your oranges due to gravity. They have those. You know what I'm talking about? Yeah. There's a relationship. Okay. So really, what's happening? This thing is all hanging. I put my oranges in here, and then it's pulling down. It's really just using Hooke's law, right? It's really just pulling on a spring and motion. The amount that needle moves is based on how far that spring stretches. Is there a word that means this thing? Okay? If I take this whole setup to the moon with my 3 oranges,
Yeah.
and
It's not a word we
hang
use a
it there
lot.
and on the moon,
I don't
is it going
love
to
that
measure
word
the same amount? No.
because I feel like
Does
it's
that
a
make
pretty
sense?
misunderstood
Because
one.
but the moon isn't going to pull down as much
The inertia,
as
which
the
is
Earth
this
is.
idea, right, of resistance.
So the oranges are less expensive on the moon,
More mass than they had is.
right? Because they're not. I don't have as much, like right? Unless you're buying them like each, and then I guess I don't know why you put them on here, right?
Or
so
you
if,
know,
if the
right?
oranges are
So-
whatever, so much per pound, better to buy them
Can
on.
we change the word motion to something that would be
Okay.
a little bit more specific, that would
I
be a
guess
little
there's
bit
that whole
more
like import tax issue, whatever.
accurate?
And that's whole economics. We don't care about that. But the
Acceleration.
actual
Why don't you
cost
change
would
that?
be
'Cause
way
the
cheaper.
two things that were kind of bubbling around in
on
my
the
head
moon,
that
if it was
it
just
could be,
based on
would be like acceleration or velocity. Is that making sense?
Why did you say acceleration? So we're going to measure our weight using a scale.
Let's write this down because this is important. You've known this for a long time, but it's not trivial, so we want to make sure we know. Okay?
Does that make sense to you guys?
Mass
That's like
does
that fundamental definition we were talking
not
about for ages, right?
change.
Yeah.
So, but that's absolutely right. So it really is a resistance to based on the force of gravity or the acceleration. Okay? Very true.
Very true.
But weight does.
Okay, so now we're getting down to the last 2 tables, and it's kind of cruel because we've already done stuff. Do you have other things to add? Everything that you were thinking is up there already?
Okay.
That scale is going
What
to
about you
change
guys?
values, whereas my
add or is
patterns
that-
will not.
Okay. So I got this little handout to give you. It's
So you're feeling good about this list.
It's a little bit silly. Cool. All right,
this is a
I made
really
it when
good
I was a student
So
teacher,
here's the
and I thought that it
weird
was
thing.
pretty good. I don't mind it.
This is
I
kind
still
of
think
a
it's
funny way to go
valuable, so
about
that's what
this
we're going to spend a little time doing.
The truth
So let's take a look
is that
at
mass in
at
and of
this. I guess
itself is not
maybe
a
the
thing.
color is even better, right? If you can
What?
actually see Bart in color.
Dang
There he
it!
is.
All right.
I know.
So
But
let's just
there's
look at
some
what's
reason
going on
there that
here.
you fill us out for a little
Okay,
bit, and
we're done.
then we'll
See
talk.
ya.
No, well, actually,
The game
there's more
here
to it.
is determining
The thing
parts
that is
of
interesting and
weight.
different is that they're actually
So
weird
Parkinson is
concepts.
going
Ready? Here we
on
go.
a ride in
different
glass
kinds of
elevator so we
mass.
can see him. Yay, hi Bart, there he is. There
Yeah,
exists
and 2 different
he
kinds
happens
of
to be
mass.
standing on a bathroom scale. Weird. It's something that
That it's a very subtle
if
truth.
you ever have an opportunity to stand on a
And
bathroom scale,
it's something
you know
that,
what it is.
honestly, before AP Physics 1 came into being, I never spent any time talking about this. But when I looked through the AP Physics 1, like, gotta know this, gotta do this, gotta do this, like, yeah,
First
gotta know
class.
this. So
We'll
that's why
do
we're
one
spending this
together.
5 minutes to have this
We're going to
conversation.
draw arrows
So let me tell you the 2 different
indicating
kinds of
the forces
mass.
acting on Bart.
So we're gonna do that first column together. He's standing still, no motion. Tell me. Okay.
Acting on
The
Bart.
first one is called
What forces are
gravitational
acting on
mass.
him in this picture.
Raise your hand if you can tell me one. Ooh, pick me. What? Gravity. Tell me what that is.
And the reason that I didn't just start off by saying
the force of the
Yeah,
earth on
you
Bart.
guys-
Here we go. Where's
the
that
mass?
by the way? Is because
Down,
what you
straight
said
down
here
is
in
center
this
of the
list
earth actually leads
that's the
us
force
to
of the
both
earth.
points. Okay.
on
The
Bart.
idea of gravitational mass that we're talking about.
Any
has
other
to
forces
exactly
acting on
this
Bart?
thing. Okay. This idea that mass is
There's a
different
normal
weight,
force.
but
Now,
they
you're
are
not
related. On the floor, though, he's standing on something interesting. What's he standing on?
Gravitational mass is mass that
That's
comes
what it
into
is. It's the
being
force of the
because of a
scale
gravitational force up on him, right? So basically what it means is that we are comparing the force due to gravity, so it would be like the Earth on an object, for example.
Determine the net force that Bart experiences.
Of an unknown
in
mass.
this one.
What's his net force? 0. How do you know? To the force due to gravity on an object. I'm gonna put that. Of known mass. I'm just gonna keep that in mind.
The strength of the Earth's gravitational field. What does that mean?
You do this.
I'll tell you.
With a balance. The Earth's gravitational field.
So do you
that
remember the triple beam
means.
balances? You ever played
What's
with
the
bread where
acceleration
you
due to
move it
gravity?
over?
So you can change that if you
Here's
want.
the secret, guys.
This really means.
that's just it's just
What's
a
the acceleration due to gravity?
measurement. Remember that meter stick with the
What is the
with
acceleration due to
masses
gravity?
on one
In
side
that
and we're
first
getting it
picture.
to balance? It's the same thing.
9.81, right? So
9.8.
triple beam balance. I should go run and grab one. Let me go do that real quick. Pause this for just a minute.
And it says
Gravitational mass.
that Bart has a mass of 65 kilograms.
So we do so.
If he has a mass of
Using a
65
balance.
kilograms, what will the scale read?
It doesn't have to be a triple beam balance, but that's often what we use. Okay? If you use an electronic balance, okay, so let's make it 10. Shall we do it? Make our life easier?
It's just that it's calibrated already.
10 meters per second squared. If you don't like that, you can get your calculator
like
out.
a
But
change
the scale's
in
going to read something about
resistance from that
600
push down or something like that. to
50
make
what?
the electric circuit
newtons.
vary what that known
Okay.
mass is.
Okay. So
The
the
other
other thing that
thing
you need to know
Okay.
about gravitational mass
For this bottom one,
is
you
that
can just
when
tell
you're
me the
measuring
thing that's
gravitational
equal to
mass,
650. Okay?
you have to you need to measure
Have a conversation with your table mates. Work on this together.
the object at rest. Okay?
All
And
right.
you can only
Let me
use
ask,
gravitational
my friend.
mass
How does? Are we okay to move on? Is that okay?
if
I'm
there is a
sorry.
gravitational
I didn't
force.
even ask. Or do you need another couple seconds? Couple
Active.
seconds. I'm sorry.
If
be
there's
couple
no
seconds.
gravitational force,
You can't measure gravitational mass. It's in the name, right? So,
no gravitational
How does-
force, no gravitational mass.
this free body diagram
Some gravitational force.
weighs really constant
That okay?
velocity compared to this one.
Okay, so that really
Same.
matches up
How does
with this definition
free body
that we talked
diagram
about right
compare
there.
to this one? These two fit into this one in a very nice
Larger
way.
force
So
up
these two are
on this
pretty
one?
similar, right? This is
Are there any
this
extra
is quantifying
forces?
it a little bit more specifically. Okay. This one is basically saying the same thing though. The amount of stuff that you've got. Okay. What did you say? And this piece here
Not on Barton
is the
itself,
other
right? Definition or the other
this one
type
has scale
of
and
mass.
earth.
Let's
This
talk
one
about
has
what
scale
that
and
one
earth,
is.
and this one's the same. I'm just going to write that down so we don't forget. Number 2.
So you're telling me this one's the same. It's called inertial mass.
This one is going to be the same except what?
Inertial mass is probably related to inertia, right?
Bigger
That definition
force
we
going
just
up.
talked about. Okay, and I'll come back to the rest of those in just a second.
The resistance of an object to acceleration.
So the force of the scale, okay, is just going to be bigger. Inertial mass is really than the force of the Earth. Nice. I mean, they're both fine. It's not like one is better.
I just got ahead of
than the
myself.
other.
Let's go back to the
It's
positive velocity.
defined
What's his net force?
specifically by Newton's second law.
0.
What's the strength of the Earth's gravitational field? Or as we know it, Newton's first and second law. What's
Okay.
the scale read? But the part that we care about is the part that they usually talk about as the second one. Okay. You guys aren't like, oops.
Impressing me with your
F equals
confidence
MA.
here. Is everybody okay with this one before we move on? The
So next,
idea
I'm
for
loud.
inertial mass, so you
So
take a
who's
mass
here?
and you apply a net force to it. So we agree on this. And
Yeah.
if you apply a net force
Talk
to
to me
it,
about
then
the
what's going to happen to it?
acceleration. Oh, excuse me, the
It's
net
gonna
force, my
accelerate,
bad,
right?
net
It's gonna have
force.
acceleration. If you know how much force you apply,
It's positive, it's
and you
going
can
up,
measure
something
the
like that.
acceleration,
Yes, net force is up, net force is positive. You can notate that however you want. You're not going to turn this in. This is just for thinking.
okay, that's exactly
Thinking
what we do.
purposes. Tell me what the strength of the gravitational field. So we're going to apply a known force. Same. Okay. Tell me about the scale reading. It's going to be greater measure than 650 newtons. Did he gain weight?
Like ate a bunch of donuts right as he was. No, he didn't. Right, but he's accelerating upwards, and so
Unlike
apparently it
gravitational mass,
appears that he's
as
as
though
though
the
he
object is
has
at rest.
increased his weight, even though
Would
his
the
weight is
object
exactly
be
the
at
same.
rest
His mass
in
is
this
exactly
case?
the same. You with me there? Yeah. No, why not? Greater than he's accelerating, right? Does that make sense?
Yeah.
So we have an object at rest,
Yeah,
there's no
we're
net
doing
force, so that's not going to be. You're not going to.
Tell me about this one.
What's
What's
going
going
on the next
Okay.
one?
How does the free body diagram compare? So it's going to be measured while the object. Yeah, so
Is
the
accelerating.
scale is going to be pushing up less in this case, right? And the Earth pushes down
Fair.
more. So they're the same two forces.
It's a very subtle difference.
The net force in this case is
This
which
is the
one?
frustrating part, or maybe the reason that you've perhaps never heard. Has anybody ever heard this stuff before? You can
Have you ever heard
always
this
give a
before?
complaint. Okay, so the subtlety is there, but the reason we don't usually spend a lot of time about this
You
or
are
with
tr-
this
you are correct.
is that because according to all physics that we know, good job.
There's
I
no
would lose
difference
points on my AP
between an
exam.
object's gravitational
Thanks for
mass
catching that.
and its inertial mass.
Appreciate it. Sweet. All right.
Okay.
Tell me
So
so
that
that
means
means
that
that
if I take this
frog
frog
and I've used the
in that
balance
one.
to figure out its mass, and then I apply a force to it and measure its acceleration.
Still same, right?
The mass that I get either way is going to be the same. Tell me about the scale reading. So why do we care, right? That's how I've honestly.
It's
always
less than
really felt about it.
650.
Okay, well if they're the same,
So
then
you
who
lose
cares?
weight,
right?
Loses weight.
Right?
Apparently college
So I
board
keep
cares.
thinking that some
Apparently
year,
they want you to know
right
this.
around New Year's,
Okay.
you know, and
The
all
thing
those,
that
like,
I really want you to
weight
know
loss
is
commercials
that you
come
don't need
out
to
on
worry
TV,
about a whole heck of a
some
lot,
Sort of
okay?
buy some money and just be like, oh my gosh, right? If you just ride that elevator downward all the time.
For all
while it's
cases
accelerating down.
that we're aware of right now,
Like,
okay?
it's amazing, right? Not permanently.
Gravitational
You
mass
just keep accelerating downwards forever, and then you keep losing weight. That's good. We okay?
is equal to inertial mass.
He's close to. It's not like he's going to the moon. He's just on an elevator.
It's just that
And then I tried to
sometimes
trick
one
you,
is
apparently.
easier to
That's
measure than
the
another.
rumor that's going on over here.
I didn't do anything.
And it is important
Tell
to
me about
keep
the forces
track
acting on Barnett.
of what's going on and which one you're measuring.
Just the Earth, right?
There is
This is just for you. I'm
no
going to draw it
difference
really, really
between
well
them,
from the
given
center
what we know
of
so
mass
far.
of Barnett. Is that better?
There are some theories, some kind of crazy
Okay.
theories out there that
Thanks for-
imply that there's
thanks for
actually
being
subtle differences.
Sweet, I got
And
one
those
out
subtle
of five.
differences
Yes,
mean
all
something,
right.
something,
Any
big
other
something,
forces
something,
acting
space
on
time
Barnett?
stuff. Okay, we just smile and say, okay.
No.
Yeah.
Nothing
okay.
else is touching him.
The only difference,
And we got the gravity. And there's none of those other crazy kind of forces.
net force acting on him, is in how you measure. It's down, and in this case, I'm going to just say with certainty that it's equal to the gravitational force. Okay, I'm just adding that just like for our own purposes. Tell me about the acceleration due to gravity. Still 10. Say that one more time. Tell me what the scale reads. Oh my gosh, it's like he doesn't exist. 0 newtons. But we don't have to be
Bart
accelerating.
is
That
what
fog has
in this
gravitational
case?
mass. He's just
He
sitting
is
there. He's not
weightless.
accelerating anywhere. Does that make sense? Yeah, so that's a
It's a
thing,
little
right?
bit of a subtle
He
difference.
is weight.
The other piece of it
Literally,
is
what does
that
that mean? It means
when
that if we
we
try to
deal
measure
with these
his weight,
things,
it looks
that
like
the
it is
distinction really comes into play
zero.
when you start to talk about
Okay?
what, like
There's a very,
Well,
very
space-
common
space travel
misconception
and
in the
talking
world.
about gravitation
Okay, we
not
talk to
as
people
everything
that if
being
something is
attracted to the
weightless,
Earth,
that means that there
right,
is no
right,
what
different
acting.
objects attracting.
There's no gravity.
Does that make sense?
So the subtlety is
A
there.
lot
but
of people
I
believe
don't
that
want
if
to get
something is
too big out of
weightless,
shape about it.
there is no
The
gravity,
questions
and
that
in
I've seen, I'm
fact,
just gonna
it's
kind of be really
exactly the
blatant about this.
opposite.
The questions that I've seen, both
Gravity is the
and
only thing
We
active.
talked about this when I was in college too.
Gravity is
All
acting
the
on
questions
Barnett,
are
it's also
about
acting
how you
on the
measure.
elevator
What
and
kind
on the
of mass
scale.
are you measuring?
Everything is
Are
falling
you
at
measuring
the same
gravitational mass? Are you
rate.
measuring inertial mass?
And because it's falling at the
That's-
same
that's
rate,
the
it
big
appears
deal.
that he doesn't have any weight.
So mass.
Okay?
Let me write that down really quick and then I'll answer your question. Is that okay? I just don't want to forget to write it down. So weightlessness really means
The acceleration.
that
Yes.
what we're unable
And that's it.
Yeah.
That's it. Yes. That would be a very simple
To
way
measure.
to define it, right? Yeah. You apply a force to an object,
the weight
and it accelerates, and the relationship between those two
because
things is the mass.
anything that we
That's
would
definition
use to
of
measure the
inertia.
weight, any scale,
Life is good. Okay. So what we're going to do today
is
for the rest of the
also
day is to use
falling.
this idea, I guess, kind of these two ideas together
Falling down
to figure out what in the world gravity
at the same
is,
rate.
because we're just
Okay.
going to do big questions today. What is mass? What is gravity? Right? We're going to solve all of the words problems right now. That's good. Okay. Okay. So questions on this one before we keep going. My next big question for you is
but you couldn't measure.
the gravitational mass in this case.
Well, we've kind of talked about it, but I'm going to ask you anyway.
Accelerating me, right? Look at that, pulling that all together. Go ahead.
What is weight?
He ended up getting the scale under him.
We've talked about it for a second, but I just want you to write that question down, and I want you to write down a definition for weight. Go ahead and do that real quick.
It would be. If you've ever been to one of those amusement park rides, they have the one that I can never remember the name at Adventureland that I love, right? Where you sit there and it shoots you up in the air, and then you sit. Yeah, space shot is that what it's called, right? And then you're sitting there, and you're like, oh look, Des Moines is so pretty. Des Moines is so pretty. And they're like, oh my gosh, right? You know what I'm talking about? Because it drops. And just for a moment at the beginning, you know how your tushy just kind of like leaves the seat there just for a second? Okay? Imagine you're sitting on a scale, right? So let's say instead of just sitting on the seat, you bring yourself a scale, bring that scale to Adventureland, put it on. They probably wouldn't allow that. They'd probably be like, no scales on the space shot. Too many physics teachers have tried this already, right? But imagine you're sitting on that scale. So while you're going up on the space shot, that's what I should do. Forget this elevator business. Space shot, right? As you're going up on the space shot, you feel like you're, right? You're like being pushed way down. Doesn't it feel like you're being pushed down? Okay? That's really just this situation, right? So you gain a whole bunch of weight. You tell somebody that, like somebody who's like really concerned about their weight, they're like, oh my God, I would never ride that ride anymore. Ah! But really, it's just because weight is a very subjective thing, right? You with me there? Okay, so they gain a bunch of weight, and then you're sitting there again. You're just sitting there. Oh, you're not at the same weight, and then you're gonna go straight down. You're gonna be weightless. You are weightless. That's that weird like feeling you get in your stomach when you're falling at the acceleration of gravity, just briefly. And then it slows down a little bit, and then your butt hits the seat again, and then life is good. You know what I'm saying? But yeah, that's exactly what's going on. So even if his feet were underneath the scale, it would all still be measuring 0. Does that make sense?
Why
Go.
isn't it the same thing for the accelerating down? That's what I was going to say.
Here? No, here.
Yeah.
Because he's not accelerating down fast enough. So he's accelerating down, but if you're not accelerating down at 9.8 meters per second squared, there's still going to be a force up.
Well, isn't the scale accelerating down at the same rate? So.
But the scale is feeling a force up from the floor. The scale is accelerating down at the same rate that Bart is, but the scale is so the way that a scale works, right, is that it feels a force from the floor up and from the person down. Are you with me there? And so if the floor up is still bigger than the person down, then it's going to measure something. Does that answer the question you're asking? And did you have the same question? You guys have like a mind meld thing going on? You just want to make sure the question got answered? Yeah.
For the last column, FG is just going to be 650.
650.
The same
Yes.
as
No,
the same as the scale.
yes. Let me make sure I agree with that. The net force down is just, yes, mass times acceleration of gravity. Yeah. Does this make sense? Other things before we keep going.
So net force and free fall is the same as weight in understanding still.
In equilibrium. Yes. You could say that. I don't think I would take time committing that one to memory, but if that makes sense to you, then that's great. Is that okay?
Yeah.
Okay. Okay. All right, so this weightlessness thing is important, okay? When astronauts are floating around, okay, you with me there? When they're floating around in their space station or they're floating around in their space shuttle, is gravity acting on them? Ask 9 out of 10 people that somewhere on the street, they'd say no. There's no gravity in space. I would say I really hope there is, otherwise we're not going to be going around the sun anymore. Okay, the gravity is what keeps us going around the sun, right? Okay, and then you think about the moon. Is the moon, what's the moon being held in circular motion by? The Earth's gravity. And if there's no gravity out at the moon, well, then we don't have a moon anymore. Are you with me there? Okay? Space shuttles orbit a whole heck of a lot closer than the moon, right? It's a big deal to go to the moon. It's a big deal to orbit the Earth, but we're not nearly that far away. So absolutely there is gravity. Yeah?
Well, the reason why we don't feel like the sun's gravity or any of that stuff, it all ties into the whole circular motion thing we just did with just the inward force.
Yeah, you guys have heard of Isaac Newton before, yeah? Yeah, I'm gonna get us there. Is that cool? Okay. Isaac Newton, he's a smart guy. Not my favorite guy in the world, but and actually this is why I don't like him. Isaac Newton discovered. Wrong answer. Discovered means that it didn't exist before. Isaac Newton did not discover gravity, friends. That would imply that prior to Isaac Newton coming up with this theory, everyone was floating around. Woo! Isaac Newton's like, gravity! Right? Like, that did not happen. That doesn't make any sense. Isaac Newton did explain gravity in a way that no one had before. That I'll give him. The reason I don't like him is because he explained it to himself and then held on to that knowledge for it was something like 8 years or something like that before publishing or talking to anybody about it. And he wrote to somebody, or there was some sort of thing about how he thought it was so exciting that he knew this and nobody else did. Like, what a jerk, right? I know this, nobody else does. That is I don't like that. That's not the only reason I dislike him, but that's, just one little taste of it. This is one of the things he thought about. So you guys know the story of Isaac Newton, right? And how gravity just came to him. What's the story? What was he doing? Something with apples, right? Making an apple pie or something. No, what was he doing? Sitting under an apple tree.
Right? So this is the story. It's not really true. But it makes for a nice, like, you know, tale to tell children. Right? So he's sitting there under the apple tree, and the apple falls and hits him on the head. Oh, gravity, I get it. That's not really what happened. But some people do attribute that idea. So the story that makes the most sense to me for a AP Physics 1 audience would be to say that he was sitting under an apple tree and he watched an apple fall. But while he did that, he was actually looking up at the sky and looked up at the moon. He was watching the moon. He thought it was so pretty. Okay, so he sees this apple fall. He knows because they've been dropping things for a long time before Newton. Okay, they've been dropping frogs for a long time before Newton. It wasn't like he was the first one who was like 9.8. No, that was like way before him. Okay, but he looked up at the moon and he said, oh, if the frog falls, the apple falls, does the moon fall also? Are you with me there? That was the big question that Newton asked. That was the question that no one had asked before, and that's what made him famous for this stuff. Okay? Because he asked a question that no one had asked or at least really explored before. So this is a little picture. I'm going to try and illustrate it from his like big book on gravity. Here it comes. You're going to draw this too. There's the Earth. Okay? This is not a real photograph or anything like that, but it's a picture. There's the Earth, and I'm going to draw a mountain on the Earth. There's my mountain, not drawn to scale, right? This is drawn to make a point. Okay? And we're going to imagine somebody up on that mountain with some frogs or maybe some cannonballs or something. I like frogs better though. Okay? And so we're going to imagine what's going to happen if this person with this frog launcher starts to launch frogs. Okay? So at first they're standing on the top of the mountain, you know, just kind of standing there. They throw the frog, projectile motion, yes? That's not a surprise to us. We've been doing that since, well, before my daughter was born, and that's been at least 6 months, so that's a long time. So there we go. So it goes like this, boom, and it hits the ground. Okay? So then we get a little bit better frog launcher. We're going to launch it a little bit more. It's going to go, yeah? Okay? All we're doing is giving it more horizontal velocity. That's all we're doing, so I'm going to, kick it up another notch. It's going to fall a little bit further, and a little bit further. Yes, are we okay here? So in this case, all of these things are going to zoop, zoop, zoop. They're just going to keep falling. But I'm going to give it enough kick that same frog is going to keep going. And he's falling, isn't he? He's falling towards the center of the Earth. Come on, there it goes. But what happens? The Earth is not there anymore. Are you with me there? Okay? So he's falling, going at a constant speed tangentially, right? That X direction, if you will. But the ground just keeps falling out from underneath him. So what's going to happen to that frog? Where's he going to go? Yeah. And so that's when you have to make sure you're wearing a helmet, like a frog-safe helmet, so that when that frog comes back and hits you in the back of the head, okay, or maybe you duck, so it just keeps going around and around and around, that frog is just going to orbit the Earth. Are you with me there? Okay? That's all an orbit is. That's all it is. So an object in orbit, I can't spell, try that again, is just one that is falling with a tangential velocity high enough that it keeps missing the ground. Okay? Or the ground keeps falling out from underneath it, or something to that effect. That's all that an object in orbit is doing. Okay? So you know that the International Space Station is up there, right? Okay? And the International Space Station is I can't remember exactly what its altitude is, but it's high up, but it's not like anywhere close to like the moon's distance away, okay? And it's just up there orbiting. So all it's doing, if we draw a little free body diagram of the space station, there it is. What forces are acting on the space station?
Gravity.
gravity, the force of the earth, right? Where does that pull? Towards the center of the earth. Okay? The force of the earth on the space station. Any other forces acting? Any other forces acting? No. It's got some tangential velocity in that direction. If I just stop the space station and then I let go, it's going to fall, right? Just like the frog. But because it's got some initial velocity in that direction, it's just going to go in a circle. Does that make sense?
So when they launch it, they have to launch it at a precise...
They launch it at a higher velocity, and then they use rocket boosters to get it into the proper orbit with the proper velocity. But once it's got that velocity, it's just going to keep, yeah.
So
Does that answer the question you're asking?
if the moon stopped, it would come to Earth.
Absolutely. Yeah. Do you have some sort of evil genius plan to like stop the moon? Or will you at least give me a heads up before you do that? So, astronauts on the space station, there they are. Whee, they're floating. Why do they float?
Because gravity's the only thing I don't know.
Because what?
Gravity's the only thing I don't know.
Because gravity's the only thing acting on them. And is it only acting on them?
Well, everything's up. It's everything.
Yeah, it's acting on the space station itself, right? Yeah, so just as those people are falling, right, so you've got the little person inside here, if we zoom in, right, so here's our little person, they're falling, I'm falling too, but the space station is also falling, everything is falling, so just like Bart on here, right, it appears that he can float around or she can float around. It's kind of cool.
Why don't they lose horizontal velocity?
Why would they?
Air resistance?
Is there air out there?
I don't know.
I think it's past this.
There is no air. It's past the atmosphere.
Okay.
Yep. So there is gravity. Absolutely, there is gravity. There is no air out there. Yeah. If you tried to do this, that's why this picture is not really realistic, right? Even at the top of the highest mountain on the Earth, okay, there's still air that would slow this thing down, so it wouldn't actually do that. But the idea is there.
What about like space junk?
What about it?
Isn't that kind of a problem now?
Sure, but what's your question?
Does it ever hit the space station?
Probably. I don't know. I mean, I don't know. I don't know enough about what exactly your question is to answer it.
Wouldn't that eventually just slow it down?
Well, there's probably ways to avoid actually impacting with it. I mean, I don't think that they're just like, just like blindly, like, whoa, right? Like I think that they try to avoid hitting things, or try to avoid having things hit them. Yeah. The other thing to remember is that most of the space junk that's out there isn't falling down; it's in orbit. So everything's in orbit, and because everything's in orbit, as long as you know where everything is at any given moment, then you can predict where it's all going to be. That's the kind of cool.
If you're is there like a very precise velocity that you go in orbit? What if you're going above that? You just still stay in orbit?
Why don't you hold on to that question for just a minute? Is that okay? Because we're going to get to something, and I want to make sure we get there that will kind of help to answer that. Okay. All right. So, what about all this stuff? So let's talk about what Isaac Newton did, what he thought about, how this all kind of fit together. Newton says, is the moon falling? And if it's falling, if the moon is falling, is the acceleration due to gravity constant? Because it's pretty constant on Earth, okay? We know now that the higher you go up on a mountain, it's going to change a little bit. But at Newton's time, we didn't know that. We thought, drop your frog, you drop your frog, you drop your frog, wherever you drop it. Given the tools that we measure, I mean, like, honestly, if I gave Cole this frog and I gave him a stopwatch and I told him to go measure the acceleration due to gravity on the top of Mount Everest, and at the lowest point in Death Valley, he's going to get about the same every time, right? Because, sorry, your reaction time, I mean, it's good, but it's not that good. It's not that good. Even if you had a partner to help you out, right? Like, we didn't have a lot of technology at the time. So this is the way that Isaac Newton got through this. And what I want to do in the next little bit here is to actually walk you through his thought process. You are as smart as Isaac Newton. Ready? We're going to do it. Here it goes. First question, question 1, to address, to help figure out this answer, right here, is how far would the moon fall in one day? So I know that the frog falls a meter in a certain number of seconds, okay? My question for you is, how far is the moon going to fall in one day? It would be the same as if the frog was falling in one day, right? How far is the frog going to fall in a day? Can you figure out that answer?
Because, like, the moon is sizably different size than anything on the Earth.
Center mass. Center, it's not rotating, so all we care about is center mass, center mass. How far is it going to fall? That's what I want to know. Go. You can do this. This is not a hard question. These are kind of silly big questions to get us there, right? I'm not saying that this is like super practical question. Very far. How far does it fall?
864.
Wait. So what did you get for the time? So the time is 24 hours, right? Which is how many seconds?
60 square. Well,
86,400.
yeah.
86,400. Okay. 86,400 seconds. How far does it fall in that much time? It's a long way. What did we get? 4.2 times 10 to the
Meters.
Do we agree with that? Yes or no?
Yes.
I don't think that's what I got. That's why I'm confused. 24 hours
No,
times.
I didn't score 2.
You didn't square t? Okay, that's going to make a difference. Square t. That sounds better to me.
3.7
Times 10 to the what?
Yep.
That makes me happier. Yes. Does that sound, that okay with everybody? Is that matching what you got? Gotta square that time. Time squared matters. Okay. That's how far the moon would fall in 24 hours. If the moon is falling. The moon is falling. But I'm going to tell you that the distance between the moon and the earth center to center, we were able to measure it a long time ago. By the time of Newton, they knew this. That it was about, well, they knew it was about 4 times 10 to the 8th meters. So it like hit us and go through and go past, right? So, moral of the story from that really quick calculation is this can't be right. This can't be 9.8. Are you with me there? Okay. So now we know how far it is going to fall. So that's the next question. Question number 2. Question number 2 is, how far does the moon fall? And the nice part about this is that if we can figure out how far the moon does fall, like geometrically, then we can figure out what the acceleration is. You with me there? If we know d and we know t, we can find a. So let's figure out, I'm gonna put this in here, in 24 hours. How are we going to figure that out?
Just goes around once.
Does it go around once in a day?
Yeah.
What's the period? Is the period of the moon 24 hours? What is the period of the moon? Does anybody know? So I'll tell you that the calendars used to be based on the lunar cycle, right? So it's about a month. It's 28 days. It takes the moon 28 days to go around the Earth. Okay? So the period is 28 days. And to save you from having to do a bunch of other stuff, I'll tell you that that is 2.4 times 10 to the 6th seconds. But you're on the right track, Sam, about thinking about how to go about this. If this is the Earth, and this is the moon, and if that's the moon on day 1, day 2, it's going to be somewhere here. Does that make sense? It's going to have gone through some arc of that circle. We want to know how far the moon falls. If it wasn't falling, it would go in a straight line. Does that make sense? Okay, if we turn gravity off, okay, Brock has some sort of evil way to turn gravity off now and then. Is that true, Brock? Or have I exposed everything? Kind of. He's like, kind of. Haven't mastered it yet, but I'm working on it. Okay. If we turn gravity off, then, whoa, hi, what's going on there? There we go. Then the moon is going to go, and it's a straight line to there, because it's got this tangential velocity thing. Why? Like, what have I done to you? Nothing. Nothing. Is that better? There we go. Stop being goofy. Why? I don't know. I'm just going to do this on the board. It's got a velocity going like this, yes? Is that okay? Okay. I want to know how far it's going to fall here. Can you figure that out? Maybe? This is really just a projectile motion problem. Oh yeah, I love projectile motion. dx equals vxt, right? Figure out how far it's going to go in this direction. Okay? We can make ourselves a nice little triangle. Triangle looks like this. And like this. Whoa, I don't know why this thing hates me today. Come on, team. And like this. That's a nice right triangle. I know this distance. I told it to you a little bit ago. You can figure out this distance. Yeah? It's a right triangle, so you can figure out this distance, your blue distance. Yes? And then from that you can figure out this. Go. I believe in you. I'm going to write down those steps one more time just so you can remember what it was. Okay? This is the distance from the moon to the Earth. Okay? That had a value of 4 times 10 to the 8th meters. This is the distance in the x direction that we would go if there were no gravity acting. So that's going to be the velocity in the x direction times time. That time is going to be 24 hours. That velocity you can figure out because you're clever. Because you know how far it goes around in 28 days. And you know how long it takes to go around in 28 days. In 28 days, right? Okay. Find that blue part. Subtract off the distance it falls. Go, go, go. You can do this. I believe in you.